Hello, welcome to this week's Naked Scientists with me, Chris Smith, and with Kat Arnie. Hello, Kat.
Hello, and this week we'll be hearing about a shocking vaccine that could help allergies, a 3D printer that can make a gun, and the invisibility cloak that can hide objects from detection by radar.
Plus, we go viral as we take a look at the emerging infections which are challenging hospitals around the world. We'll find out where new flu viruses come from, we meet the strain of TB that's almost untouchable, and we look at how Twitter and other types of new media are now being used to track infections as they spread.
If you'd like to get in touch with us here at The Naked Scientist, just email studio@thenakedscientist.com. You can tweet @nakedscientists or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
And joining Kat and me for a look at what's making science headlines this week are Patrick Walter, he's from Chemistry World magazine, science journalist Mark Peplow, and physicist Laurie Winkler, she's from the National Physical Laboratory. And kicking off, Kat, an electrical vaccine for allergies.
Yeah, is there anyone else here suffer from dust mite allergy? Because I do, it's horrible. Anyone else?
A few people here with a cold. I know you're sniffing, Mark.
I am, yeah, but no allergies, thankfully.
No, I have terrible dust mite allergy, so I was very interested in seeing this new paper that's come from researchers in Thailand working with a company in the US, and they've taken a step forward in developing a DNA-based vaccine that could actually go forward for testing in clinical trials for people who have allergies to house dust mites. Now, this is an allergy that affects up to 1 in 5 people in industrialised countries, and it's the leading cause of asthma. Again, that's something that does plague me. Now, over the recent years, scientists have tried to cure allergies like this by exposing sufferers to tiny amounts of the proteins that trigger their reactions. I'm sure on the show about a year or so ago, we covered peanut allergy that was trying to be cured with tiny amounts of peanut flour. Now, the idea is that these small amounts of the allergens, the proteins, stimulate helper immune cells. These are called Th1 cells that damp down the overactive allergic immune response. But unfortunately, actually building up this reaction can take years, and there's a risk of triggering a massive allergic reaction by accident. And so they've been writing in the journal Immunology Letters, and the scientists have developed a vaccine based on a tiny fragment of DNA, and it encodes the instructions to make a protein called DRP2 that's found in house dust mites.
So when you say that they've actually got a DNA vaccine, what does that mean practically, Kat?
So how it works is it's a tiny fragment of DNA that has the genetic instructions that makes this house dust mite protein, and you inject it into the muscle. So far this has only been done in mice, but there are similar DNA vaccines in other diseases such as cancer. So you inject the DNA into your muscle, and then you give it a little electrical shock. Now, this isn't sort of a massive zapping, but it's an electrical shock that kind of stuns the cells a bit and makes them take up DNA that's around them. It's usually a technique, if anyone's a scientist listening, you might have done this in the lab to make things like bacteria or cells in culture take up DNA, but it works in real living things, including humans as well. So they gave this little piece of DNA to some mice, gave them a little zap, and they found that actually it really did work to help reduce their allergies. These were mice that had a model of house dust mite allergy, and it worked really well. It sort of activated the helper cells and damped down their immune responses.
So the piece of DNA gets taken up by cells in, say, the muscle. The electric shock helps that. The muscle cells then make the gene product, which is the dust mite allergen.
They make the little dust mite protein inside their cells, and that's just a small enough amount to kind of trigger the immune system to recognise it and get the helper cells going, so that then when the body sees the allergens in real life, the helper cells start to damp down the allergic response. And certainly in mice, it looks like it's achieving the desired effect. So the next step they're hoping is to go forward for clinical trials. But obviously this kind of immune system mucking around at the edges of the immune system is quite controversial. It's quite risky. So I think, unfortunately for me and certainly other dust mite allergy sufferers out there and asthmatics, it's going to be a little bit longer before we get to a clinical trial, I think.
Mark?
But why can't they just inject the allergen protein itself?
Well, this is being done with some other types of approaches. So there's people working on peanut allergies where you give people tiny, tiny, tiny amounts of peanut flour over a long, long, long time. But you have to do it over years, tiny, tiny amounts over years to build it up in the right way. For some reason, it looks like doing it with a DNA-based vaccine where the cells in your body make this protein. It seems to be a sort of short circuits that process and gets the immune response sorted out a bit quicker.
I hope they can do that because, as you said, asthma is really common and dust mites are a major cause of it. So do they indicate how long this will take to translate, or is it just because it's already an established approach, there's no real reason why it couldn't go forward?
It's more quickly. At the end of the paper they say, we think this should go into clinical trials. So
they just need a few £1 million and they'll be there. So they're
working with a company in the US, but obviously, there are some big risks when you start to tinker around with people's immune system. So I think more work to make sure that it is safe first.
Very interesting. Thank you, Kat. Now, Patrick, you have got a way to stop me and maybe the rest of the world drinking tea, which I've made, unfortunately, with mouldy milk, assuming my nose isn't good enough to smell it already. But, what's the serious message here?
Well, Chinese scientists have developed a packaging sensor that you slap onto, say, your milk carton, and it tells you how old the milk is and also what kind of conditions it's been left in. Has it been left out in the sun for too long?
This doesn't sound like a particularly new idea, though. I'm sure I've heard statements or sort of aspirations to have food labels that will indicate whether food is off or not in a packet. How does this one differ?
Well, this one's very good because it's very simple, it's straightforward, it relies on a relatively cheap mechanism, so there's no electronics involved like some of the other sensors.
So tell us, how does it work then?
So this particular sensor relies on plasmonic phenomena. At the nanoscale, things like metal nanoparticles can behave rather differently from at the bulk kind of levels. So gold nanoparticles appear red rather than, as you would expect, gold, and this is down to a plasmonic phenomenon. So why does this happen? This is because light interacts in unusual ways with these nanoparticles. So as the light strikes the metal nanoparticles, they set up an oscillation or a wave, and this can reflect or absorb or scatter light depending on the wavelengths coming in. So what they do is their sensor is based on gold nanorods, and in the gel with the gold nanorods is silver nitrate and a reducing agent, in this case vitamin C. So what happens over time is that silver ions released from the silver nitrate start to plate the gold nanorod, and as the nanorod gets covered, the plasmonic characteristic of the nanorod changes. So you're covered with this silver, so you get a different kind of reflection of light. So it goes from red, the silver gradually builds up orange, yellow, green, and that's when when it goes green, that's when you don't want to eat whatever is there. You don't want to be pouring that milk into your tea.
What makes it do the colour change then? This is the key thing. How does that tell me how the food has been handled or stored, that colour change?
Well, the colour change happens over time, and this time can be set by varying the levels of the nanorods, the silver nitrate, that kind of thing. But what's also very important here is that it's the temperature. So the warmer it gets, the faster the reaction goes, the faster the nanorod gets covered with the silver and the sensor turns green.
So it's actually only a measure of temperature, which is a useful proxy for how food has been kept, but it doesn't by any means tell you this food is safe or not.
It doesn't, no. But it tells you, has your feckless supermarket attendant perhaps left your meat out in the sun too long that morning rather than putting it straight into the freezer cabinet? So for things like meat and seafood, it can be very dangerous if they get warm, because then you get a build-up of noxious, nasty bacteria that can give you a bad case of food poisoning.
So temperature is important. More importantly, at the moment in British supermarkets, can it discriminate beef from horse meat?
If only that was the case. You're still going to have to send your horse meat off to the labs for a bit of PCR.
DNA testing. But actually there is a historical aspect to this, isn't there? Because of course if you look at the same science, you find this manifest not just today but for hundreds of years.
This is definitely true. The artisans who made stained glass windows were unwitting nanotechnologists. What they did was they included metal salts with the glass as they made it. And so things like gold chloride gave you a nice ruby red colour, silvers gave you green, and things like iron gave you, I think, kind of greens and browns. There's a really nice cup, a green glass goblet in the British Museum that was Roman 4th century, I think. And it appears green in normal light, but if you stick a nice bright light actually into the cup, what you get is the cup goes this nice red colour. It's really worth a look if you can find the time.
I should give it a look. Patrick, thank you very much. Kat.
Now, we'll hear more from our news panel in a moment, but first, 3D printing is a technique that's dramatically reduced the cost of building complex plastic objects in recent years. Now, you may have heard that this week in the US, the first ever shot was fired from a gun that was built using 3D printing. Now, here's your quick fire science about the technology from Naked Scientists Elena Tay and Pete Skidmore.
3D printing involves building up an object by stacking up many layers of material rather than carving bits away from a solid block.
It means that you can make one-off personalised objects quickly and simply.
To print an object, a 3D image is first created using computer-aided design programs.
The program then creates digital slices of this 3D design, with each slice around 0.1 millimetres thick.
The printer then converts these digital slices into layers of a printed material, usually plastic, and builds successive layers on top of each other.
When plastic is used, it is fed into the printer as long, thin strings. It's then heated until it melts and can be printed as a liquid, much like using a hot glue gun to make patterns on a surface.
The maker of the gun printed each plastic component individually and then connected them together. The only metal component was a nail, used for the firing pin.
Critics are concerned about the production of the gun, as the digital design will be made freely available online.
Some British companies have also warned that the material has not been fully stress-tested and could disintegrate when firing.
Other methods of 3D printing involve using a fine plastic powder, which is held together using an inkjet-printed glue, or using a laser to melt metal powders together to build metallic objects.
It's not just small objects where 3D printing is becoming useful. It's a low-waste method of building structures, and some people are even starting to think about printing houses.
I'd print myself a new overdraft. Kat.
At the moment, I'd print myself a new car because mine's in the garage. That was Pete Skidmore and Elena Tay. Now, Laurie, you've also been looking at 3D printers, but this time producing something a little less controversial than a firearm. What's your story?
Yes, Kat. There was a paper about a 3D printed cloaking device. Now, I'm not going to say invisibility cloak because, well, we'll talk about the different light sources in a second, but this is not a Harry Potter cloak. I'm just going to preface it with that. A group in Duke University have actually built, using 3D printing, a cloaking device that is capable of rendering objects completely invisible to microwave light. So not visible light, so microwave light. And they've done this much more cheaply, much more quickly than these cloaking devices have previously been produced by using this low-cost stereolithographic polymer-based fabrication, or 3D printing. And it's actually based on some research that the same university carried out a few years ago. They showed that if you were very careful and had very precise control over holes in a surface, in a disc, you could actually, instead of getting a shadow cast on an object, so you shine light on an object and cast a shadow behind it, or having light actually bounce back or reflect from the surface, you could actually deflect light around an object. And by doing that, you render it invisible. So what they've actually produced is a cloaking device that does this, but with microwaves.
Laurie, first of all, how do they know where to put those holes in the device?
The thing about microwaves is they have a particular range of wavelengths. And by knowing that wavelength and doing a lot of mathematical modelling, you can kind of optimise the size, the shape, the positioning of these holes so that they deflect only microwaves. So it's all to do with the wavelength of the light that's actually being shone on the object that you're trying to hide.
Does this mean that you could take another material with different properties that would work for visible light? Because microwaves is one thing, but that's not that useful, is it? If we wanted to really hide things and have a Harry Potter invisibility cloak, we would need something that would work for visible light.
Yeah, absolutely. That's the big challenge. They think that with the measurements that they've done and the models that they've carried out and the experiments that they've run, they think that they can actually extend this to visible light. So the first thing you need to do if you want to cloak something from visible light is to find a material that's already or as close to invisible to our eyes as we can. So transparent objects would be the kind of obvious one to go to. And you also need to have, because you've got on invisible light, you've got much shorter wavelengths than you do with a microwave. And that, remember, defines the size and shape of the holes that you need. If you move down to shorter wavelengths, you need much smaller, much more precise hole positioning on this cloaking device. So you've kind of got two separate challenges. But this team believe that it's actually, again, moving towards nanotechnology might actually be able to answer both of those issues.
Maybe an invisible car for Cat will also have to wait a little bit longer. Mark Peplow, you've got something about helium?
Yeah, that's right, Chris. The fate of one of the world's main sources of helium is about to be decided, and whatever happens to it, we can be pretty sure that helium is going to get a lot more expensive.
Why?
Well, debate is going on at the moment in America as to what to do with the US Federal Helium Reserve. The US government has been socking away, or had been socking away helium in there since the 1960s, until it had accumulated about 1 billion cubic metres of the gas by the 1990s.
Where on earth do you store 1 billion cubic metres of helium?
In the ground. Natural gas is found in the ground in porous rock, so they've literally been pumping it into an emptied sort of gas field as a way to store it. Now, why do we need to store helium in that way? Well, it's incredibly useful for things like liquid helium, because it's so cold, minus 269 degrees C. It cools the superconducting magnets that you find in things like medical imaging scanners. And the semiconductor industry uses it to shield crystals that it uses during manufacturing of computer chips, things like that. And, of course, it goes into party balloons as well. Let's not forget that. So this basically in the 90s, the US lawmakers decided that the US government was going to get out of the helium business. This reserve had accumulated a huge amount of debt. It said, sell off the helium, pay off the debt, shut off the taps. We're not going to sell this stuff to the commercial market anymore. That debt is due to be paid off in October. And yet the reserve still accounts for about a third of global helium supply, which is about 170 million cubic metres a year.
Whoops. So what have they said they're going to do then?
Well, lawmakers are now trying to get a bill, an act that will actually stave off that closure, that will allow helium to keep flowing probably till the end of the decade. But that goes hand in hand with selling off the helium at much higher prices. One of the reasons the commercial market isn't going to be able to take over quite yet is because helium from the Federal Reserve was being sold off dirt cheap. So there wasn't a lot of incentive for commercial extractors to actually develop more sources. So now the helium is going to be auctioned off at a much higher price, close to a genuine market price. And that's overall going to lift up the market price of helium probably by 30% next year.
Isn't that going to incentivise the opening up of other possible helium sources?
Yes, it is, and there are new sources coming on stream in Qatar. Russia are likely to start exploiting helium in Siberian gas fields towards the end of this decade. So yes, it is incentivising people to go after more helium, but that is going to go hand in hand with price rises. And we can be sure that hospitals that use these in MRI scanners, researchers that require helium for low-temperature physics, are going to have to start planning ahead for factoring in those cost rises.
Mark, thank you very much. That's Mark Peplow. Also, thank you to Laurie Winklis and Patrick Walter. You can find more information about the stories we've been discussing, including the references to the original papers, on our website. That's at nakedscientist.com/news.
Now, you're listening to The Naked Scientist with me, Kat Arney, and with Chris Smith. Now, steel is the most widely used metal in the world. In 2011 alone, around 1 billion tonnes of it were produced worldwide. But the steel industry accounts for 5% of the world's carbon dioxide emissions. Now, this week, a team based at the Massachusetts Institute of Technology revealed a more environmentally friendly way of producing it using electricity.
And to comment on the work, we're joined by Derek Frey, who's a metallurgist here at Cambridge University. First of all, what's the process by which we actually make iron that leads to it producing so much CO2 every year?
Well, it's reduced by carbon. Carbon is an excellent reductant, and it's very, very plentiful. As you know, we're used to burning in our homes to keep the homes warm.
And we're doing that by chucking carbon into a furnace, and the carbon's stealing the oxide off of the iron to leave molten iron.
It ends up as CO2 eventually.
What's the aspiration, then, to try and get that CO2 down? How could we do it better?
Well, this team at MIT has discovered a means of electrically reducing iron oxide at very high temperatures, about 1600 centigrade, which is more than white heat. So they simply dissolve it in a liquid solution and electrolyse it.
Now, what is electrolysis?
The iron, when it dissolves in the electrolyte, as it's called, is there's iron ions and oxygen ions. And when you pass an electric current through the solution, the iron ions will go to the cathode, discharge and form iron, and the oxygen ions will go to the anode and form oxygen gas.
But we do that with aluminium oxide, don't we? We make aluminium metal by electrolysing bauxite, which is aluminium oxide. So why can't we just do that for iron?
Well, the problem is that, in the alumina case or the aluminium case, you also produce a lot of carbon dioxide because they use a carbon anode. So the team at MIT, their goal has been to produce an anode which you can evolve oxygen on, and you get pure oxygen generated. So there's no CO2 from the actual decomposition of the iron oxide.
So the problem that they had to grapple with was what sort of material to use to do that electrolysis, what to use as the electrodes.
Mm-hmm.
So how did they approach that then?
The approach they adopted was to essentially use stainless steel. Stainless steel is usually iron, chromium and nickel, and what they did, they used an alloy which is iron and chromium, plus a few other minor elements.
So you mix those two things together. Why don't they just melt when you dunk those materials into molten iron oxide? Why don't they turn into just liquid
The
iron?
melting point is higher than the temperature of the electrolyte.
So what happens to these electrodes? Why does this work where others have failed then?
Well, it forms a very tenacious oxide film, which doesn't dissolve in the electrolyte, and it's conducting, so you can pass the electrons to and fro through it.
What forms an oxide layer where? Just talk me through what's going on in this electrolysis cell.
When you put the iron-chromium alloy into the electrolyte, it oxidizes it a little bit. You get a very, very thin layer, which is very stable, so it doesn't dissolve.
So that forms on the surface of the electrodes, and this protects the electrodes from the environment they're in. So what does this mean in terms of how we would actually deploy this?
It would be very similar to the whole aerosol for the reduction of alumina, where you would have a liquid metal pool, you'd have the electrolyte floating on the top, and then your anode would be above that. So when the oxygen forms on the anode, it just escapes.
Could you do this in a batch process, or would you have to chuck a whole load of the oxide in and then run the electricity through it and reduce it to metallic iron, then pour that off and start again? Or could you continuously add little bits of iron oxide and keep the process going all the time?
Well, if you go back to the whole aerosol, essentially that's a batch process. It's the aluminium is taken out about every 8 hours, and you feed the alumina in about every 8 hours as well.
If we actually do this, why is this better than doing it the traditional way with carbon? Because the electricity is presumably going to have a carbon cost attached to it, isn't it?
I think the assumption would be the electricity would come from photovoltaics or wind power or sea power or tidal power. Obviously, if you're having to use electricity from a coal-fired power station, the savings aren't as great.
Does the discovery of this new material actually mean something in terms of how we could use it in other areas, though? Because not just for iron. Could it be used elsewhere? You
could use it for other metals.
What about the fact that it also makes this oxygen? Is that useful?
Probably not on the Earth, but it would be in the solar system or on the Moon. The rockets that took the astronauts to the Moon, 20 or 30 years ago, they were mainly oxygen. You need about 80 tons of oxygen, about 10 tons of hydrogen for the power. So if you obviously hope to bring the astronauts back, you have to take enough oxygen up there. And if you could generate the oxygen on the Moon, it would be very much easier. So
in other words, if we could take moon rock and use this sort of technology, these sorts of electrodes, and electrolyse moon rock, it would be very nice because we could get other metals out as well, which could be good for construction.
Things, yes,
but we would also then get a supply of oxygen to send people off on other journeys or even bring them home, which is jolly nice.
Because the advantage of the moon is the gravitational field is 1/6 of that on the Earth, so you need less power to escape the gravitational field.
OK. Thank you very much. Derek Frey is from Cambridge University, and he wrote a news and views on that article, which is published this week in the journal Nature, which is where the original research is also reported. Kat.
Now, if you want to get in touch with any questions or comments, you can email studio@thenakedscientist.com, you can tweet @nakedscientists, or you can find us on Facebook.
Now, we live in an age where modern medicine largely makes us feel like we've won the war against bugs. But with bacteria and viruses constantly evolving, new infections regularly emerge. Later on, we're going to be talking about how we can track these new epidemics using medical mapping, as well as how our old enemy, tuberculosis, is making a comeback.
Now, first, in March, a brand new strain of the influenza or flu virus called H7N9 was detected in China. In the months since its detection, 100 people have been infected and a fifth of those have died. We're joined in the studio by Dr. Colin Russell from the Department of Zoology at the University of Cambridge, who's an expert on how viruses like H7N9 can evolve to become serious threats. So, hello, Colin.
Hi, Kat.
Hello. Now, just explain, what is H7N9, and why is it different from previous flu strains?
So H7N9 is an influenza A virus that is not fundamentally dissimilar to the H5N1 virus or the bird flu virus that we've been so concerned about over the last 15 years. Now, H7N9 is of particular concern because it's something that we haven't seen infect humans before. And prior to March, we hadn't seen this virus in any humans ever. Now, since that time, we've seen 130 humans infected with the virus. And of those, approximately 20% of them have died. And so in these particular circumstances, where we have a new influenza virus emerging in the human population, it is, of course, of serious concern.
Because I'm sure all of us know about the massive flu pandemics. And before we come to talk about some of the scary stuff, I just had a question. Why are these flu viruses called H something, N something? What do those letters designate?
Well, all influenza A viruses are called H something, N something, because influenza viruses are characterized by the proteins that are on the surface of the virus. So there are two proteins on the surface of the virus. There's the hemagglutinin protein, which gives us the H, and the neuraminidase protein, which gives us the N. And there are 16 known hemagglutinins in birds and 9 known neuraminases, which can give us a tremendous number of combinations of viruses that could cause infections in humans. But so far, we've only seen H1N1, H2N2, and H3N2 cause pandemics in humans. So the fact that we now have an H7N9 virus causing infections is something new. Now, along these lines, we've also seen H5N1 viruses infect humans too, but we've never seen massive human-to-human spread of any of these viruses other than the H1N1, H2N2, and H3N2 viruses.
So why this new H7N9, why does it seem to have such a high mortality rate? Why does it kill proportionally more people than some of the other flus?
Well, as compared to the known cases for H5N1, bird flu, this H7N9 virus is comparatively less lethal. So for H5N1, there's been about 600 known cases so far, and approximately 50% of those cases have resulted in mortality. Now, in the case of H7N9, we have a situation where we've seen about 130 cases to date, and about 20% of those have died. But we don't know that there aren't cases that we don't know about. So in this particular case, we could just be seeing the tip of the iceberg.
Where did this virus actually come from? Because it's originated in birds, as bird flu did as well. Where do we think it started, and what created it?
Well, this is a good question, and it's one at the tip of everyone's tongue right now, because we don't really know where this virus came from. Now, there are some things that we've managed to learn about the virus from analyzing its genetic sequences. So myself and many others have looked at the genetic sequences of these viruses, and we found that these viruses are actually the product of 3 different influenza viruses. So influenza viruses, their genes are each coded by individual segments of RNA. And they have 8 genes in total. So the H gene, the hemagglutinin, and the N gene, the neuraminidase, account for just 2 of those 8 genes. Now, we know that the H gene came from an H7 virus and that the N gene came from an N9 virus. But interestingly, the internal proteins, these are the ones that aren't on the surface of the virus, all appeared to have come from an H9N2 virus. Now, interestingly, when we look at the genetic relationships among these viruses, we see that the internal proteins, those that came from this H9N2 virus, all are most closely related to viruses that either came from wild birds or from poultry in the areas around where the original cases emerged. So we have a good sense in this particular case that we have at least seen the geographic region where the earliest cases have emerged.
So there's been some kind of genetic mix and match going on in a bird to make this new virus. So then it sort of spreads in birds, I guess. How does it get from birds into humans?
Well, that's a good question as well. So for influenza viruses, there's a particular term for this. It's called reassortment, because the influenza genes are on each on different segments. The viruses, if they co-infect a host, the genes can get all mixed up or reassort.
Then mix and match, basically.
Exactly. Now, but in the context of how it gets into humans, in the case of this particular virus, we don't really know where it's coming from. I mean, we certainly suspect that it's coming from birds, but we don't really know. Now, for H5N1, we have a much better picture of how humans typically get infected. And the majority of individuals who've been infected with H5N1 over the last 15 years have been in close proximity to either fowl or domestic poultry. So there's a particular story that I like, which involves, it depends on who you hear the story from, a Thai duck farmer. And this Thai duck farmer lives in his home with his ducks, and he has a duck that has flu-like symptoms, because frequently when birds get highly pathogenic avian influenza viruses, they have the same sort of symptoms that humans have. They cough, they sneeze, they have a runny nose.
Sit in front of the telly all day,
Well,
terrible.
you know, if you've got a telly and your duck likes it, there's no reason not to watch it. But basically, this farmer, he sees his duck is suffering, and this just isn't agreeable to him, and he really wants to help. And of course, you can give a duck a tissue, but you can't make it blow its nose. And so he decides that he's going to help. And he does the only thing he can think of, which is he puts the bird's beak in his mouth and he blows.
Oh, no!
Now, this, of course, causes an evacuation of the bird's nostrils directly into the man's eyes. Now, one of the things that's really interesting about this particular case is that one of the primary reasons that we don't see bird viruses crossing into humans all the time is that bird viruses have a different cell surface receptor that they bind to, apart from what normal human influenza viruses bind to. But interestingly, we have those bird influenza receptors in our lower lungs and in our eyes.
Oh my God, so you basically have to get bird snot into your eyes.
Well, bird snot into your eyes would be one way to do it, but otherwise you need to get the virus deep into your lungs, which is not a trivial thing to do.
You have to be breathing in bird snot, basically.
Or you definitely have at least very
breathing
close
in very
contact
heavily
with
around
birds,
birds.
indeed.
But now about this new, the H7N9, do we know if it can transfer between humans? And we know it can go from birds to humans, but what about from human to human? Because that's when stuff gets really scary.
Well, that's when it becomes of increasing concern. Now, right now, there are no known cases of human-to-human transmission. And the Chinese government is doing an extreme amount of work in order to trace all of the contacts of the individuals who have been in close proximity with individuals who have tested positive for the H7N9 virus. And so far, none of these secondary contacts have tested positive for an H7N9 infection, which suggests that we haven't seen human-to-human transmission yet. But that only involves the cases that we know have been, that have shown up in hospital.
So there may be people out there with it that are just sick and haven't been kind of ticked off on the, oh, you've got that. I mean, should we be worried about this now that we've identified it, and we seem to have identified a group of people that have it as a general population, and obviously we're in the UK and not in China. Should we be broadly worried about this or not too worried?
Well, there's two causes for concern. So one, any time where we see a new influenza virus that is infecting more than a handful of people, it's a cause for concern because, of course, in the past, influenza viruses that have crossed from animals into humans have caused pandemics. Now, in this particular case, we've seen a fair number of human cases in a relatively short period of time. So, of course, that is a cause for concern. Now, another cause for concern is that these viruses appear to have mutations that, at least in the case of H5N1, could lead to easier transmissibility between humans. Now, that said, we still haven't seen human-to-human transmission yet, but because these viruses have some of these mutations, there is cause for concern that it might be easier for these viruses to evolve to become transmissible than other influenza viruses that we've seen crossing into humans in the past.
I guess we'll just have to watch and wait. Thank you very much for scaring us all to death. That's Colin Russell from the University of Cambridge.
And this is The Naked Scientists with Katani and with me, Chris Smith.
If you've got any questions about emerging infections or any of the other topics we've been discussing in today's show, email us at studio@thenakedscientist.com. You can tweet @nakedscientists or find us on Facebook.
Today, quick transport links between cities mean emerging infections can spread globally very rapidly. So scientists need a way of following the course of the disease. And Pete Skidmore has been finding out how medical mapping provides an insight into the dynamics of disease spread.
Plotting the spread of disease onto maps is an essential tool for governments and health organisations trying to stem the tide of epidemics, because it allows them to plan where resources such as vaccines and sanitation will be most useful. To find out more, I spoke to Dr. Tom Koch, a medical geographer from the University of British Columbia in Canada.
Medical mapping as a consistent tool in the study of public diseases began in 1796 with a study of yellow fever. It is the way in which we take a collection of events and then we plunk them into a specific geography where we can test the relation between the occurrence and the environment that either promotes or inhibits it.
Thinking about the modern world now, obviously there's a lot more mobility between cities. There's a lot of figures going around that no city is 24 hours away from any other city. Is there any way that we can adapt to cope with the different epidemiological factors with a much more mobile society?
Globalization really is just a speeded up version of the mercantilism and then the industrialism which has long been in place. But it was really the Crusades that traveled between cities which brought us the plague in the 14th century. It was globalization and it was trade and it was the passage of people from one country to another which brought us cholera in the 19th century. So the first thing to recognize is this is nothing new. It might have been speeded up some, but it's a difference of degree and not kind. What the rapidity of travel means is it will be even harder, despite all of our vaunted technology, to stop either the evolution of our microbial friends or the progression of the disease that they eventually hit upon.
Infections may be able to spread across the world more quickly now than at any other time in history, but surely with the advances in global communication and social media, it's easier to track epidemics. I spoke to David Piggott, a DPhil student at the University of Oxford, who studies the different ways we build disease maps.
We believe systems such as HealthMap and Biocaster, GenBank and potentially social media can help. HealthMap and Biocaster are websites that use data mining algorithms to trawl the web looking for non-conventional data sources. So they look at news articles, other websites that wouldn't ordinarily come up if you're using a standard academic literature-based search engine. And combined, they're bringing up about 400 new posts every day pertaining to different diseases. And then finally, Twitter and social media at the minute represents an uncertain but very promising route nonetheless, where we can use the tweets if they're relating to a disease, for instance. That would be the hardest task, trying to identify what keywords are critical for which disease and try and use information from that. But Twitter is a very noisy system when it comes to disease reporting. Previously, people have identified that Twitter trends for influenza and dengue predict trends in case reports from conventional systems like the CDC in America by up to 2 or 3 weeks before. So it has the potential to help, but we need to do a lot of work to determine the accuracy of those data points.
So you mentioned Biocaster and HealthMap. Have these at all helped in the recent epidemics, like H7N9, SARS-like coronavirus?
So HealthMap and Biocaster have been used in that, particularly just picking up news reporting in China, for instance. But yeah, given there's a lag time between case reporting and National Health Service reporting level, it's the hope that HealthMap and Biocaster could try and reduce that lag in delay, especially when it comes to a very novel infection where actually it's the speed of information gathered that's the most important aspect.
So where will the next pandemic come from? Tom Koch has the answers.
We know that the next pandemic is almost a certainty, I would say, within 10 years. And it will start, as pandemics always do, in a type of area which is densely settled, where there is huge social and economic inequality, such that there will be a dense group of people living in poor surroundings, often with their animals, and that it will spread from there to a primary city and from there to other primary cities. So it may be that it starts in China or Vietnam, places where we have huge densities and huge income inequalities, and then it will spread with travelers first in a local area while the virus or bacteria gets set, and then it will grab an airplane and fly on off.
And is mapping prepared for that?
Sure. As the data comes in, we can map it and we can very quickly predict, depending on the nature of the specific microbe, its rate of diffusion to primary and secondary sources. We know how to do that. More important is, can we and why are we not identifying the places where the disease is likely to come and putting our international energy into the type of development which will limit the opportunity for the virus and bacteria to proliferate, mutate, and then spread.
So new diseases are constantly emerging, but hopefully new methods of mapping them will allow us to stop them in their tracks.
We've been hearing a lot about new infections, but sometimes old enemies come back to haunt us. Tuberculosis, TB, is a disease which many of us think of as a thing of the past, but now it's back on the rise in the UK and elsewhere in the Western world. And part of that might be down to the recent discovery that TB can conceal itself in cells in our bone marrow, even in people who've ostensibly been cured of the infection. We'll hear more about that in just a minute from Stanford physician Dean Felsher. But first, consultant microbiologist Sani Aliu is with us to talk about another emerging threat from TB, which is that the bug is rapidly becoming resistant to the majority of the antibiotics that we use to treat it. So, Sani, first of all, what actually is TB and why is it such a problem?
So TB refers to tuberculosis. It's been with us for quite a while. It's an infection caused by a bacteria called Mycobacterium tuberculosis. It usually manifests with cough, respiratory symptoms, fever, night sweats, and could affect any organ in the body really, but mostly the lungs.
How do people catch it in the first place?
Transmission is usually called airborne, simply because when you cough or when you sneeze or you talk, you have droplets that contain the bacteria. And the droplets can survive in the environment for prolonged periods of time. They tend to be suspended, and if you inhale the droplets, the bacteria goes into your lungs, and then you get infection. By inhaling the bacteria, you don't necessarily get active disease. You can get latent disease because 1 in 3, it's estimated worldwide that 1 in 3 people are infected with TB. So it's very common.
When you say latent disease, what is actually going on? So you've been infected, but you don't have TB actively growing in you. Is that what you're saying?
And that's right. So you've been infected with the bacteria that's sitting dormant or latent in your body cells, and it's hidden. May not necessarily come up and cause symptoms. It's only when you have symptoms that's when you have tuberculous disease. Although most cases of active TB arise from the latent form, where you have the bacteria replicating and then causing symptoms, usually in relation to immunosuppression or old age.
And what does it do in the body? Does it just cause chest disease problems, or does it go elsewhere too?
TB can affect virtually any organ in the body. Severe tuberculosis, for instance, can affect the brain, can affect the meninges, so you can have meningitis. It can affect the bones. In the past, what we call Pott's disease, where you have people with infection involving the spine, has been well described. You can also have genitourinary tuberculosis, abdominal TB.
Now, when people talk about drug-resistant TB, first of all, how do you actually treat normal TB? What's the regimen?
The first drug that was produced and that was found to be quite effective for TB was streptomycin in 1944. And since the 60s, when rifampicin came in, TB has been treated with a cocktail of at least 4 drugs. They're called first-line drugs. So here in the UK, for instance, we have rifampicin and isoniazid, which are considered the core and most powerful anti-TB drugs available. Then you have paracetamide and ethambutol. You could also have injectables.
And you give those for quite a long period of time, don't you?
That's right. For pulmonary disease, you give the cocktail of drugs for a total of 6 months.
And what's the reason why TB is now no longer responding reliably to that cocktail of drugs?
So a combination of factors, really. What's been happening since early 90s for the last 20 years is we have a large cohort of people, especially in the middle and low-income countries, where you have tuberculosis that's not really being treated properly. You have both misuse and mismanagement of the drugs. If you have patients with tuberculosis taking the drugs in a way that they're not supposed to, either taking one pill or taking an inadequate dose or taking for a very short period of time, you tend to develop resistance simply because you have that drug pressure which pushes the bacteria to develop mutations.
And so What is the status of TB response to our medication now? How many cases of TB would we regard as resistant?
So worldwide, we have what we call multi-drug resistant TB, which essentially is resistance against the two core drugs, rifampicin and isoniazid. It's estimated by the WHO that there are probably about 65,000 cases of multi-drug resistant TB, mostly in high-incidence countries such as sub-Saharan Africa, the Indian subcontinent, and Central Europe.
And what about the more resistant form, the XDR TB that we're now beginning to hear about, extensively drug-resistant TB? How's that differ?
So extensively drug-resistant TB is really a progression of MDR TB. In other words, in addition to resistance to rifampicin and isoniazid, you also have resistance to a class of antibiotics called the quinolones and to at least one injectable antibiotic. And what this confers is really a difficulty in managing the TB. You have to give a cocktail of drugs that are usually second or third line drugs that aren't as effective as the first line drugs. You have to give them for a longer period of time. They are much more toxic, they are more expensive, and it's a nightmare, really.
And how common is that form of TB?
Fortunately, in the UK, pretty rare. In 2011, this is based on information from the Public Health England website, which has more recently called the HPA. There are about 81 cases of multi-drug resistant TB up to end of 2011, but only about 24 cases of XDR TB in total, of which 6 were confirmed in 2011. So it's still a pretty rare disease, fortunately, in the UK.
But it's not zero, is it? Which means we need to keep an eye on that. Thank you, Sani. And Dean Felsher, now you've recently shown that TB can hide away inside the body and remain in a viable state even in people who have been what we would regard as cured.
Right. So what we found was that tuberculosis can hide in a very unexpected site. It can hide in a rare population of bone marrow stem cells that have the special name, mesenchymal stem cells. And they have multiple biologic properties that make them a perfect place for tuberculosis to hide away. They like to migrate around the body. They're naturally drug resistant. They're naturally resistant to the immune system. They can tolerate living in a low oxygen state, which is typical of places where tuberculosis infects. So in many ways, they represent the sort of perfect host cell. It's been known for a long time that tuberculosis can hide in other normal cells in the human body, but this population of bone marrow stem cells was rather a surprising finding that we reported recently.
How did you discover that TB was lurking in those cells?
So our work has very much been interested in the role of stem cell and stem cell kind of biology in disease processes. And there was the very creative idea that tuberculosis may be taking advantage of a normal stem cell population. And I decided to pursue this by studying whether or not tuberculosis could live in normal human stem cells. And we were able to show that indeed they could preferentially infect and become dormant in these normal human stem cells. And then we're even able to show evidence that this was true in human patients.
Now, first of all, talk us through how you think the TB gets to those stem cells in someone who gets infected via the lung or breathes in some TB, and then what happens to the TB once it's in the stem cell?
It's known that tuberculosis will form a structure that we call a tuberculosis granuloma. And other scientists had reported that some of the body's stem cells like to migrate to the granuloma. And what we think happens is that these special type of bone marrow mesenchymal stem cells are attracted to the site of infection, and that tuberculosis has figured out a way to get into these cells and then use them as a way to escape the normal sorts of mechanisms that the host immune system is trying to use to get rid of the tuberculosis.
So those cells get infected in that site in the lung, and then they go back to the bone marrow, do they?
They can go back to the bone marrow because they're capable to migrate as well as go to other sites.
And how do you know that once the TB is in those cells that it's actually viable and that it remains in a viable state so it can come back to life from within those cells later?
Yeah, we were able to take from patients who had been treated extensively in a way that you would expect they were cured of tuberculosis, people we knew had tuberculosis, take their bone marrow out using a special procedure that we use as hematologists called a bone marrow biopsy, and purify this subpopulation of bone marrow stem cells and show that we could not only detect the DNA of tuberculosis, but we could actually recover viable tuberculosis using microbiological assays in the laboratory.
So these are people who've had drugs that have cleared them of signs of being infected with TB. They would be regarded as cured, but actually you can get stem cells out of their bone marrow and there's viable TB living in there.
Exactly.
So what are the implications of that?
Well, the implication is that it may be that if we can figure out a way to get rid of tuberculosis from these bone marrow stem cells, we might be able to come up with a better long-term treatment for tuberculosis.
Well, let's hope so. As Sani says, with 1 person in 3 carrying it, we need to move fast, don't we? Thank you very much to Dean Felsher from Stanford School of Medicine, and also before him, Dr. Sani Aliu, who is from Addenbrooke's Hospital in Cambridge. Kat.
Now, if you have any questions on the emerging infections we've been discussing on today's show, you can email studio@thenakedscientist.com, you can tweet @nakedscientists, or find us on Facebook. And you're listening to The Naked Scientists with Kat Arney and Chris Smith.
And finally, this week, Hannah has been considering the impact of a move to the big smoke.
This week, we consider moving to the city, since Jeremy Eaton wrote in with this.
Do you have a stronger immune system if you live in a big city because you are surrounded by more people and their diseases?
So, do city dwellers have a strengthened immune system in the long term as they come into contact with more people with a greater range of bugs? For the answer, we turn to Professor Eleanor Riley from the big city's London School of Hygiene and Tropical Medicine.
So in principle, yes, people living in small isolated communities may experience a more limited number and diversity of infections, and they can lack immunity diseases which are actually quite commonplace in other environments. And some classical examples of those were epidemics of diseases such as measles and smallpox in small Amazonian communities when they first came into contact with outsiders. But these days, human populations are so mobile that actually very few of these really isolated populations persist. And you're as likely to contract the latest strain of flu whether you live in a huge city or in a smaller town or village nearby. And that's because people move around between these communities on such a regular basis that they move the virus around with them. And we only have to look at how quickly the swine flu epidemic in 2009 reached almost every country in the world, including countries with really low population densities. And we can see from that actually from the perspective of the bug, we all now live in a single global community, and our immune systems will reflect the fact that we're all exposed to very large numbers of infections.
So, with frequent global travel, there's no rationale for rushing to live in the city since it won't boost our immune systems. However, pollution and stress from the city have both been linked with weakened immunity. Plus, there's studies that show that people who grow up in cities process stress differently and have an increased risk of getting mental health disorders such as schizophrenia. Moving out now to Pastures New, Pradeep Patel wrote in with this.
I want to know, what is wind and where does it come from? Not the type of wind you get from eating lots of baked beans, but the one that we feel in our face and see in the trees.
So what is wind and why is it with us? Let us know your thoughts by posting on our Naked Scientists Facebook page. You can tweet at Naked Scientists, you can email studio@thenakedscientists.com, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
That's Hannah Critchlow there.
Well, that's it for this week. Thank you very much to our guests, Eric Frey, Colin Russell, Sani Aliu and Dean Felsher. Thank you also to Kat Arney for joining me. The production this week was by Dominic Ford and Kate Lamble. And next week, we'll be finding out how weather forecasts actually get made and what early warning systems can tell us when extreme weather might be on the way. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust and the EPSRC. I'm Chris Smith, and thank you for listening. Goodbye.